Okay, so Samir, floor is yours.
Yes. Thank you, Fari, for the introduction. So today I'll be discussing about this recent work of ours, probing the physicochemical properties of the Leo ring and the Leo 1 group. So this work has been recently accepted in MNRAS. And here is the outline of my talk. I'll begin with an introduction to the ways in which we model quasar absorption lines. I'll then discuss the data that has been used in our analysis and a Bayesian approach to modeling quasar absorption lines that I developed for my thesis work. I will then discuss the implication of the results that we have obtained and then end with some concluding remarks. So seen here is an absorption line system at a redshift of 0.08 towards the background quasar PHL 1811. On the y-axis, we have the normalized flux, and on the x-axis, we have the relative velocity, with 0 being the redshift of the absorber. In various panels, we are seeing the absorption as seen in the different transitions, starting from higher order Lyman lines H1 920 to Lyman gamma, then Lyman alpha, Lyman beta. Then the low ionization transition of the intermediate ionization transition of silicon 3, the higher ionization lines of silicon 4, the even higher ionization lines of carbon 4, nitrogen 5, and oxygen 6. So the data that we are seeing here and data of similar signal to noise and even better quality data have been amassed over the past 2 decades, both with the Hubble Space Telescope using the instruments COS, STIS, and so on, and from the ground-based telescopes of Keck and VLT using the instruments of HIRIS and US. So from all this data, a coherent and logical picture is beginning to emerge about the CGM around the galaxies. So these absorption lines that we are seeing here, they are encoding within them the information of the CGM around galaxies. But the question now arises, are we able to extract the true nature of the CGM from these absorption profiles? It turns out that in most of the literature, the properties from these absorption lines are derived in a simple manner, which involves dividing the column density of a metal line with that of hydrogen to arrive at a single value for metallicity. However, with our approach, we find that the absorption in H1 is not only arising from a single phase that is traced by silicon 2, but there are these other phases of gas. For example, in this case, there is carbon 4 that is coincident with silicon 2. There is another carbon 4 cloud that is at minus 50 kilometers per second, and there's a cloud traced by carbon 3 at minus 100. So these 4 together are producing the absorption that we are seeing in H1. So what comes out of this analysis is that these different absorption components have different origins. They have different properties. So these different properties could be differences in their metallicity. This could be inflowing gas, it could be outflowing gas, it could be altogether gas that is associated with different galaxies. So with our approach, we'll be able to paint a more truer picture of the CGM around galaxies, whereas in the former case, by obtaining a single metallicity, we'll be washing out the signatures of all these different physical processes in the CGM of galaxies. So with that introduction to how we analyze absorption lines, I would like to make the transition to the current work that we have recently published. So this is a work that is investigating the Leo 1 group, the absorption seen in Leo 1 group. Now, why was this undertaking done is that, so we have these absorption profiles that I showed you. This is an example. Now, the question then remains, are we able to extract the signatures of these different physical processes or different galaxies that are contributing to the absorption? An ideal test bed to investigate this would be something that is at very close redshifts. In this case, the redshift of this Leo 1 group is at a redshift of 0.0025 or heliocentric velocities between 600 to 1300 kilometers per second. Because it's so close to us, we have a complete census of the galaxies, even the low surface brightness dwarfs that may be present in this region. So, and moreover, this being a galaxy group, there are several galaxies whose CGM would be overlapping, and and then we can test if we are able to extract out which absorption components are related to which galaxies or the process within galaxies. So what was done in this work is that we have identified this group, and luckily we also had several archival observations of quasars in this region of space. So we found that there are five quasar sightlines which had quasar archival observations, tracing the Leo 1 group, encircled here surrounded with a box. And then in the larger vicinity around this Leo group, there were also 7 sightlines with cos observations. So on the right hand side, I'm showing a zoom of this box. And what we see here is an interesting structure of gas. So this ring of gas is called as Leo ring. This is a giant intergalactic H1 ring, the origin of which has been a subject of debate for some time now. So whether it is pristine in nature or whether it is something that has formed out of merger of galaxies has been a debate for the past more than 15 years. So in this work, we have investigated the plausible origin of this ring as well. And the colors that we are seeing here are basically the velocities, heliocentric velocities of gas, and they're indicated with this color legend here. So we have for all these sightlines cos G130M observations as well as G160M observations in some of the cases. And out of all the 12 sightlines, the average signal to noise is about 10 or lesser than 10. In the case of sightline A, the signal to noise is very poor. It is like 0.1. So we don't analyze the sightline A any further, and I'll not be discussing about sightline A. We'll be discussing about these rest 11 sightlines.
So Samir, before you move on, okay, I guess here, and also, which one is the dominant galaxy here? Is any particular, are they all equal in masses, or it's like is there a dominant 1 or 2 or 3 galaxies in the system?
So the Leo 1 group, thank you for pointing that out. The Leo 1 group comprises of these dominant galaxies of M105, M84, NGC 3412, and M96 and M95. So these are the 4 dominant galaxies that make up the Leo 1 group. So the contributions to the absorption that we are seeing along these sightlines is potentially coming from these galaxies, or it could be from the Leo ring as well. So with our work, we are trying to pick it apart and see which of these are contributing. So in this slide, I am showing these important galaxies which are responsible for which could be potentially responsible for the absorption that we may see along these sightlines at this redshift. And on the right hand side, I have shown this ring. Now, as I've indicated, this ring has been a subject of debate. But in 2010, Michel Dansac et al., they have done a simulation work where they have hypothesized that this ring is potentially has originated from a merger between the galaxies of M96 and NGC 3384. So this is taken from their simulation. I'll just play this simulation to show how this ring could have originated. So this M96 is passing through NGC 3384 there, and all the gas in NGC 3384 has been stripped off that galaxy, and this galaxy is now encircling around M105. So, and this collisional encounter, according to the simulation, has happened 1.5 billion years ago. And this is a hypothesis. So with this work, we are testing whether from the properties that we derive, whether it is pristine or whether it is from this merger event. So just to give you an idea of how the spectra look towards the sightline, I am showing you this particular spectrum. This is the absorption spectrum towards sightline C. The sightline C is here, close to the luring region. Close to the luring region, and the signal to noise ratio of these spectra is less than similar to 10. So we have G130M observations for all these sightlines, with covering Lyman alpha, the carbon 2, the silicon 2, the neutral lines, the nitrogen 1, carbon 1, silicon 4, and also the high ionization line of nitrogen 5. In some of the cases, we also have carbon 4 covered with G160M, not in this case though, sightline C. So this is just to give you an idea, and as we go forward, I'll be showing you several such spectrum towards different sightlines. Now, before obtaining these normalized spectra that I have shown here, in particular for sightline C and also for other sightlines, we had to do one pre-processing step. The pre-processing step is that because the absorption of interest is so close to us that the Milky Way Lyman alpha affects our analysis. The absorption of interest, which is between 600 to 1000 kilometers per second, happens to fall on the wings of the Milky Way Lyman alpha. So what we do is we fit a void profile to it and divide it out to obtain the normalized Lyman alpha of absorption of interest. This is I have shown towards sightline E. And additionally, there is also the problem of the geocoronal emission. So this is from the Earth's atmosphere itself. So we have to ensure that there is no flux being added to the absorption of interest from this geocoronal emission. So to ensure that, what we do is we fit air glow templates. These templates are made available by STSCI. These air glow templates were obtained by Burrier et al. In their 2018 work. And we fit this air glow template to the geocoronal emission. And we find that in all the sightlines, this geocoronal emission is not contributing any flux to the absorption of interest. So this I have shown with the sightline E, but this is the case in other sightlines as well. So now that we have the data, and we have taken care of all the pre-processing steps, the next task is to model the absorption or determine the properties from these absorption profiles. So to do that, we make use of a photoionization code called Cloudy, which is designed to simulate matter in the interstellar medium. So these models that we are seeing here are all curves that are void profile fits based off of Cloudy models. So I'll discuss how these models have been obtained. So we start off by generating a grid of Cloudy models. These Cloudy models are photoionization thermal equilibrium models having 3 different parameters. Each Cloudy model is identified by 3 parameters, the parameters being metallicity, hydrogen number density, and neutral hydrogen column density. So each point in this Cloudy grid contains the information of column densities of different ions of interest to us, and the temperature T, which is the equilibrium temperature that Cloudy solves for by balancing heating and cooling. The heating is coming from the UV radiation of all the sources, stars and galaxies at the redshift of the absorber, and the cooling is happening from radiative line transitions. So by balancing these two, Cloudy self-consistently solves for an equilibrium temperature. So with the temperature known and assuming a non-thermal broadening Doppler parameter, which is drawn from a uniform prior of values, we obtain the total broadening parameter for the absorption profile. So a Doppler parameter is basically gives the how broad an absorption is, and with that known, the column density known, and the redshift of the absorber known, we can generate these void profiles for different parameters, different combinations of parameters, and then fit with the data. So this process of exploring this cloudy grid and fitting the data is done using a Bayesian approach, which I'll be discussing now. So each cloud in the in this absorption system is identified by 5 parameters. The parameters being metallicity, hydrogen number density, neutral hydrogen column density, and the location where the cloud is centered, and a B non-thermal, which is drawn from a uniform prior. Redshift is drawn from a Gaussian prior centered at the initial VP fit that we obtain. And then these 3 terms are drawn from this cloudy grid. So to determine the best fit models, we employ Bayesian methods. And this is implemented with a nested sampling algorithm called multi-nest. We use a Python implementation of it called PyMultinest. And this is uh, particularly efficient at sampling from a multimodal posterior distribution. So what I mean by this is that in some cases, because these profiles can combine in different ways to produce the absorption that we are seeing, there could be a case where there may be two points in this cloudy grid where an equally good fit may be obtained. So it is important that we don't miss out on those different modes which are present in the data. And multi-nest is particularly adept at solving that problem. That is, it is able to find these multiple modes which may still fit the data pretty well. So to explain how this sampling works, I'll make use of this simulation taken from here for a multimodal distribution. So assume that this is a two-dimensional parameter space, unlike the three-dimensional here. So we'll assume that the log NH1 is a constant. So we are drawing from a plane of this cloudy grid. So starting the sampling, so what this does is it divides the parameter space into slices, this particular sampling method, and then draws from these different subsets, slices, and then combines them by appropriately weighting them to recover the true distribution that we are seeing here at the bottom. This is different from, for example, MCMC methods in that they directly draw samples from the posterior by not splitting into different slices. So the advantage with multi-nest is that it is unlikely to get stuck in a local minima because it is exploring these different regions in space and then combining them by appropriately weighting them. Whereas with MCMC, it is possible that we may get stuck in a local minima. So to fit the data, we do the inference with multi-nest. Yeah. Now that we have discussed the data and our methods, now I'll go on to the results. I'll be showing each the application of our method to each of these sightlines that we have here. Sightline C to sightline I, 11 sightlines. So this is sightline B. This sightline B is quite far away from the luring Leo1 group as well as the luring. So it is somewhere there, far away from the luring absorption. We see a simple profile in Lyman alpha with no coincident absorption seen in metals. So it's a simple single component profile. And on the right hand side, I have shown the properties that we have determined. Here we have metallicity, here we have hydrogen number density and the temperature. So because we don't have a handle on the metal column densities, it is an upper limit that we determine. So it's an upper limit on the metallicity. The neutral hydrogen column density is a lower limit, but the temperature, as we see, is well determined. Is 10 to the 4 Kelvin. That is because the shape of this Lyman alpha profile is narrow. So it is the Doppler parameter that is giving us a good constraint on the temperature. So these are violin plots showing where the width is the largest. It's more likely that is the value, that is the more likely value. that fits the data pretty well. So where it is thinner, it's unlikely that that will be a good fit. Now sightline C. Sightline C is close to the luring absorption. It's there. And so here we have four different components. The bulk of the absorption coming from this C2 component there. And there's also nitrogen 5, a broad nitrogen 5. We also see absorption in silicon 4 and silicon 3. And here, coming to their parameters, we see a diversity in their inferred parameters. So this nitrogen 5 absorption phase is determined to be supersolar. The red component, which produces most of the absorption in C2, silicon 2, and silicon 4, is consistent with solar. The narrow C2 component, which produces the wings that we are seeing in the H1 profile, is 110 solar. And then this is a hydrogen only cloud with no associated metals detected. So it's an upper limit again. Now, this nitrogen in 5, in this case, we have modeled it as a photoionized nitrogen 5, but it is quite possible that given the high ionization potential of nitrogen 5, it has an ionization potential of 77 eV. It's quite high, and it could well arise from a collisionally ionized phase. So we also explore models in which nitrogen 5 arises in a collisionally ionized phase. And our parameters that we determine are not very different from a photoionized N5. There is, however, a difference in the temperatures that are inferred for the N5 phase with a collisional model. It is greater than 10 to the similar to 10 to the 5.5 Kelvin, whereas in the previous case it was 10 to the 4.5 Kelvin for the nitrogen 5 phase. Similarly, sightline D is on top of the luring, and it shows two component structure with the bulk of the absorption coming from carbon 2, and it's a single component also seen in silicon 4, silicon 3, and no absorption seen, for example, in iron 2 and neutral phases. So this component is determined to be solar metallicity with this hydrogen component with no associated metals is again an upper limit. This is sightline E. So a trend may be seen from these absorption profiles. So sightline B and sightline E. These are quite far away from the luring absorption, sightline E and B, whereas sightline C and sightline D are close to the luring absorption. So what we are seeing here is that there is a kinematic spread in the absorption components for associations with the LEO1 group and LEO1 gas. But for those sightlines that are far away, we see simple structures, single component structures often. So coming to the parameters of sightline E, we again have a supersolar component and a component that's consistent with solar metallicity. The supersolar component is needed because we need to produce nitrogen 5. It's found that the nitrogen 5 also produces carbon 4, but very little hydrogen. Because it's producing little hydrogen, it has to be it's resulting in a supersolar metallicity. And then we have this very modest absorption seen in silicon 3 that produces hydrogen, and it has to be consistent with solar, but within the uncertainties, this could be a non-detection, given that it could be an upper limit as well, because we cannot rule out these other values that are there. And again, we explore a collisionally ionized carbon 4. The parameters don't change drastically, except for that the temperature of this collisionally ionized phase has to be greater than 10 to the 5 Kelvin. Then sightline F. Sightline F is also on top of the luring. Now, this is one of the most the spectrum with the least signal to noise ratio with a signal to noise of less than similar to 3. And given that, although we don't have strong constraints on it, but we do see strong absorption in carbon 2. In the neutral phases also we see absorption carbon 1, nitrogen 1. And we did an experiment to see how different column densities of H1 would affect our results. And after exploring the grid with different combinations, different possibilities of H1, given how the data is, we found that it has to be solar or greater than solar, with metallicity being greater than 0.2, the log of metallicity greater than 0.2. Then sightline G, this sightline again is on top of the luring. Now here again we see a kinematic spread in the velocities, and we see a dominant absorption coming from this carbon 4 cloud, and there's a silicon 3 cloud as well that is also seen to produce absorption. And these two clouds are found to be supersolar. Then the rest 3 clouds don't show any metals in them. They are upper limits again. Sightline H, this is also a sightline that is close to a luring absorption. Again, it shows a kinematic spread in the absorption components with the contrasting metallicities obtained in these components, and the rest two are upper limits. Sightline J, this is again far away from the luring gas. Here again we see a simpler absorption profile that's not spread out in kinematic space. So we found that a single phase is able to explain the absorption seen in carbon 4, carbon 2, silicon 3. And then there is this hydrogen only cloud, which is an upper limit. And this component is greater than solar in metallicity. Then we have these 3 other sightlines, S, I, K, and L, which don't show any absorption between the velocities consistent with the luring absorption. So this may imply that assuming the merger scenario, since the merger happened in this direction, the gas must be spread, maybe is localized in this direction only, and it's not spreading, or it has not is not being the sightlines are not piercing any gas that is there. I mean, this gas has not spread so far, or that there are no galaxies that are contributing to the absorption at these locations. So now that we have determined their properties, the next task for us was to determine which of the galaxies are responsible for the absorption in different components that we are seeing. So to do that, we use a term called likelihood parameter, which is given by this equation. It is exponential of minus rho over r variable squared times exponential of minus delta v over v escape squared. So I'll explain how these terms affect the LP, the likelihood parameter. Rho is the impact parameter of a sightline from the galaxy. R virial is the virial radius of the galaxy, and delta V is the V absorption, that is where the absorption is seen in the spectrum, minus V gal plus minus V escape velocity. So this accounts for the fact that any absorbing cloud that is within the escape velocity of a galaxy could still be associated to be arising from that galaxy. So that is our assumption here. And this is basically a modified prescription from the French and Walker work 2017. So if rho is 0 or it's very close to the galaxy, then this term will be e to the power of 0, 1. And if delta V or the V absorption is very close to the galaxy, the systemic velocity of the galaxy, it will be 0. So it will again be 1. So values that are close to 1 imply that that particular galaxy is highly likely to contribute to the absorption. So this is all the other terms like R varial, V escape are kind of simpler to determine, but V gal, to determine that, we make use of rotation maps and the stellar velocity fields in the direction of these different sight lines. I will discuss this using the example of sightline C in this case. So sightline C is there with respect to M95. Sightline C is there and the sightline F is in this direction. So we have this H alpha rotation map and we have the velocities of the gas in these different directions. So this gas is between velocities of 775 and 700 in C. In the direction of F, it is 725 to 7. So we do such a determination and then determine the LP parameter for absorption seen along all the different sight lines. So coming to sightline B, we found two galaxies that could potentially be contributing. Their LPs are so insignificant that it's unlikely that these galaxies are contributing. It's more likely that it is the absorption from large-scale intrafilamentary gas that is contributing to the absorption towards sightline B. And to sightline C, towards sightline C, we have four components towards sightline C, four different components. And with our LP formulation, we find that the galaxy M95 is more likely to contribute to the first two components, and M96 is more likely to contribute to the narrow component, that was this narrow component. M95 is more likely to contribute. So we do this for all the other sight lines. Here I am showing a pictorial representation of the. So for sightline C, we have M95 passing within the virial radius. The sightline is within the virial radius of M95 and M96. So there is a potential contribution from these two galaxies. For other sightlines, for example, sightline L, where we did not see any absorption, there is no galaxy or not even the luring gas piercing the absorption. The sightline is not piercing their absorption. Now to the absorption along all these sightlines, we have now estimated the LP parameter and determined which galaxies are contributing. So here I have summarized in these different panels the absorption, the Lyman alpha absorption seen towards all the sightlines, and the potential candidate galaxies contributing to the absorption seen in these components. So for example, for sightline C, we have M95 and M96 potentially contributing. There it is M96, and then this red hatched lines are luring contributions. So interestingly, if we plot their equivalent widths for gas that is seen towards luring and Leo 1 group, we see high equivalent widths compared to gas that is seen towards these other sightlines. So along these sightlines, because there is a contribution from these different galaxies and the luring gas, we see a kinematically spread out absorption, and that is accounting for this large equivalent widths. So a circle as big as this is an equivalent width of 1 angstrom. This tiny dot is 1 milliangstrom. Now coming to the properties of luring. So we have estimated their properties and determined which of the absorption components are associated with luring. So here I have plotted the properties: metallicity, hydrogen number density, temperature, and line of sight thickness. A thing that is consistent among all these luring associated absorption is that they seem to show solar or higher metallicities. Hydrogen number densities are between 10 to the minus 4 to 10 to the minus 3. Temperature is consistent with photoionized gas between 10 to the 3.5 to 4.5, and line of sight thickness between 1 to 10 kiloparsecs. So if one were to take an average of all these values and estimate the mass of the H1 ring, it turns out to be 3 billion solar masses, and that is consistent with the expectations from that is consistent with what is derived from 21 centimeter emission maps. So to conclude, with our component by component Bayesian methods and careful treatment of the Lyman alpha, we considered which galaxies or processes are shaping the absorption that we are seeing along each of these sightlines, allowing us to consider whether there's a coherency in properties across the region. And we do indeed see this coherency in properties for luring association. That coherency is that they have solar or greater than solar metallicities. And in each case where the absorption is detected, there is a contribution from one or more luminous galaxies in those luring associations. And in sightlines B, E, and J, it is more likely the intragroup medium and the specific interaction, which is the luring. And as our results have shown, the luring has a covering factor of nearly 1 of supersolar metallicity low density gas. The high metallicities that we infer from our absorption studies and by Corbelli et al. In emission suggest that this gas must be pre-enriched with its origin in galaxies in the region, and it cannot be pristine in nature. So it's more likely that the gas that these sightlines are tracing is something that originated in galaxies which contained within them this pre-enriched gas. So yeah, that is the main conclusion of this work. And yeah, thank you so much for listening.
Thank you. That was really, really, really interesting. And I was wondering if there are any questions from people who are around. Okay, if not, I'll start. So yeah, some really interesting stuff about this. And my question is whether you've looked at you did this likelihood analysis to try to associate one galaxy to one absorption, whatever you see in the absorption to whatever is nearby based on kinematic location and also distance in projection, right? But so like in general trend, do you see any association kinematically between the gas in the Leo ring region with the nearest galaxy from where you see the gas, or is it more complex than that? But like, if it's stripping from the nearest galaxy, for instance, do you actually see any association with the kinematics of the galaxy itself with what you see in the gas?
Yeah. So this is a plot which kind of summarizes that association, and as you have alluded to, it is quite complex because some of these components in kinematic velocity space, we are seeing that it could either be from the galaxy or it could be from the Leo ring. So the window width here that is plotted, it accounts for all the gas that could be within the escape velocity of the galaxy. We cannot do a more constraining analysis than assuming that all the gas would be within the escape velocity of the galaxy. And that kind of precludes us from giving very tight constraints, because these windows often can be as large as 100 kilometers per second, as we see here.
Okay. Okay. All right. And one other question is, so you do see some evidence that within the ring itself, the lines of sight, all the absorption suggests that the gas has been highly chemically enriched, right? Compared to like gas further out, especially like the K, the L, and the I. So my question is, did you try or did you attempt to see whether there are any, because these are quite massive galaxies, right? M105, and they are kind of Milky Way size or more massive, it looks like, from their appearance. So do you see any, were you able to kind of obtain any constraints on the abundance profile of the gas? Like, whether you're able to kind of get how the abundance of different element groups as opposed to just a single metallicity, basically.
Yeah.
So,
We were to do that, for example, in this case, cycline C, as you see, we have this coverage of nitrogen 1 as well as O1. So the N by O ratio is something that is an indicator for the enrichment history of the gas. And we start with the assumption that all this is solar abundance pattern, and with our solar abundance model and the inferred metallicities, the gas that we are seeing is consistent with originating in low Z star forming galaxies, like the galaxies that we have in this field, than dwarf galaxies, for example. So this was something that your recent work has also found. The Cubs 4 sample, and yeah, and we cannot incorporate an additional parameter given the signal to noise in our data.
sure.
We have started with solar abundance pattern and found that we are able to find profiles that fit the observed data.
Sure. Okay, Michael has a question.
Yeah, thank you. Very interesting presentation and paper. My question was, you have iron in some of these cases, iron 1143. Can you do the alpha over iron ratio for some of these observers?
Yes, yeah, we can definitely do that. But since we have started with the assumption that this is a solar abundance, and if we were to relax it and see, probably there may be a degeneracy between the ionization parameter and the abundance pattern. So in order to completely eliminate that, probably if we had access to more of the iron lines, for example, Fe1 and Fe2, and then carbon, different transitions of carbon 1, carbon 2, we do have. But given the nature of the data, maybe there may be a degeneracy between the ionization parameter and the abundance, assumed variation in abundance.
Okay, yeah, well, that's great. So, yeah, thank you, Samir, for your for this very interesting discussion, and we will meet later, and I look forward to discussing about some of this more with you later. And yeah, if anybody still wants to meet with Samir, you just go back to my original email. There's still some open slots in the afternoon, so feel free to do that. And with that, thank you, and we'll see you soon.
Yeah, thank you. Bye.